ways to measure back in space. It's easy to measure across like that. You can make equal divisions. You can use your ruler or your calipers or whatever else you want to, because they're consistent. But as soon as you want to put those back in space, equal divisions, so that they are going away from you, you can't just do that by eyeball and expect it to be accurate if it needs to be accurate. And that's what depth measuring systems are. There are 5 of them, and I'm going to give you 3 of them tonight. And let me tell you what it will require to get this tonight. It will require that you understood everything I've taught this semester up to this point. If you tonight is like judgment night. If you've been getting it at the lectures and then losing it during the week and not reviewing it, you might get lost this evening, unless you're just sharp, because I'm going to be drawing from the previous information pretty heavily to make these points. That's why I say, I mean, it would be nice to do tonight's lecture and next week's lecture, just give it to any class, because people need this stuff. But you have to establish foundation. So we've established foundation. Now we're going to get real practical and apply it. System number 1. I'm going to try to do these left to right on the board here. I may fail, but I'll do the best I can. System number 1 I call cross diagonals, or X, finds the center. You already know about this. You know that if you take any rectangle, it does not make any difference whether it's a square, a horizontal rectangle, vertical rectangle, or what size it is. The fast way to find the center is run a line from corner to corner, and then another line from corner to corner, and that's not just the center left and right, it's top to bottom. Okay, that happens on a flat surface like that, but fortunately for us, it also happens when you tip things into space. Imagine that you actually drew lines on that object to make an equal division. Now, let's make this, it could be anything. It could be a briefcase. Let's say it's a briefcase. Make it a little shallower to make it a briefcase. And we know that in the middle of that briefcase, right there in the middle, there's going to be the hinge. How do you find the middle? In space, you go like that, and it will intersect right at the actual center. Now that divides it into half. What if you know that there are also little straps that are going to come down here, and they're halfway also, but you can eyeball it. But if you find that point and then make another little X like that, you've divided it now into what? Fourths. So you can divide the top of this. Let's do another thing. Let's say that that's a ping pong table. Let's put a ping pong table into 2-point perspective. Get rid of our briefcase. And we need to find where to place the net. You can eyeball it, but it's very quick to divide this thing in half in space. The net's going to go right along there, and then you just do vertical lines up from there. Of course, that will go off to that vanishing point. That will go off to that vanishing point. You can flesh this thing out like so and put legs on it. But that will be, that front half will be more than the other half. Now, that is a quick, simple way of measuring things back in space. But it has its limitations, doesn't it? It requires that you know the front and the back edge. So telephone poles going off into infinity, it won't work with. You have to know the front and the back edge. And then there's another limitation. What's the other obvious limitation of dividing up that space? It only works for dividing into even numbers like 2, 4, You can do it into 6. You just, you leave, forget about some lines. 8s, 16, 32. You can divide this by going like that. You want to do another center line there, do the same thing, and it'll go right there. You can do the same thing, and then keep doing that. But there is one problem with that, and that's if you start to divide this into 32 parts, that's an awful lot of construction lines to find how to do it. But this is the simplest, quickest, and most limited means of dividing back in space. Now, number 2. And I'm sorry, these names might not be the best. I haven't put my energy into naming these, but I'll call this one Diagonals Find Far Corner. Forget about the name for now. It'll make sense after I explain it to you. Let's see. First, I want to do a flat diagram of what I'm getting at. You know that this divides up the center. Let's do it again here, a side view. Let's say you've got a whole bunch of telephone poles or any other equal divisions that will go off infinitely a space. A picket fence, parking meters, and there's going to be a number of them equally spaced that are going off into space. You need to somehow get them out of perspective, like we've talked about. We know how to find the middle of this one. That's this would be one pole there and one pole there. But how would we make an equal space over here? In flat, you can measure it like that, but you can't do that in space yet. Well, if that's the absolute center between there and there, wouldn't it make sense that if we wanted an equal space over here, of which this line, you've got to watch this carefully, this line will be the absolute center, that we could do this, we could find that point there and then run a line from, we want to make an X of a bigger box. Do you see how if I run through there to there, that it will intersect? Now look what I just did. I made another one of these that will be equal to that, because now you can imagine there would be a big X that would find that middle. Does that make sense? Now let me review what I just did. I was trying to find this hidden line over here by making an X through the middle of what? Through the middle of the imaginary box. I can find 2 points. They're going to intersect there, and I can keep doing that. Where will I go from here? It helps to just run that line through. From here to here, you see how that's going to intersect there, and I can just keep doing that. From there to where? Not through the middle of this box, because I already know that's just going to take me up to there. I don't care about that point. I care about this hidden one over here. So I'll go from there through there. And now I'm not making X's. I'm making a single diagonal, which is all I need. Does this make sense? Now let me show you that it works in space too. Let's take, we'll establish that pole right there. And then what have we got to do? We're going to take this back in space. This is the limitation of this one. You have to know how close you are to it. That is, what the size of the next one will be. And you can connect those lines, actually. You can see I didn't have it in adequate perspective. Now, I want to keep going back in space. Can you figure what I've got to do? Go back to this if there's any doubt. I need to find the next line. How will I do it? Well, it's easy to find the center of that one, right? But I don't care. I already know about that point. I've established this. I want to repeat it back in space. It will help to run a line through that center point back to the vanishing point. Now watch what I do. If you're drawing this, you're crazy. This is in the books. Draw it then. It's better to watch someone do it, because if you miss one point, you get lost completely. I want to go through that point, not through this point, but through this one to find the hidden missing line. Then I want to keep doing that, and they will diminish accordingly. You can make them go back infinitely. I've simply done this, but I've placed it in a perspective grid. Did it make sense? That's what I mean when I say diagonals find far corner. The biggest mistake, this is where all of you blow it when you're drawing while I'm drawing, and that you have to spend 15 minutes figuring out what the problem is. Most people, when they're trying to find this next one, will find a center point in this one right here. And they'll just find, oh, I already know where that corner is. That's not what you're doing. You're trying to find this hidden one over here, and oh, okay, it's got to go through there and give me the new division. And when it works in 2 point, or excuse me, when it works flat, it will work in 1 point or 2 point. Now, it doesn't just work with verticals. Remember what we can do? We can take the board and go like this. And then what does that become? Yeah, railroad tracks. That's right. That's how you'd measure back railroad tracks. But you do have a problem with that. Railroad tracks have thickness. So you have to decide what those lines represent. Do they represent the center? Do they represent the far contour edge? The near contour edge? If these are poles, and the poles have thickness, is that a line going through the middle of the pole, or is that a line that goes through the far contour of the pole? You've got to decide that, because you've only got one line, and that's going to have to be consistent. This works for any division. It will work for that kind of thing. You want to do more of those. You want to run that up there, and you can just keep doing that. You got to have that center line to find it. So that's depth measuring system number 2. What is it good for? It's good for things that recede infinitely at the same interval. Yes, Daniel?
If those were columns, how can you tell how thick the column goes when it goes back? How thick the column will be when it goes back?
There is a way, and that's what the next one's going to solve. There is a way to do it with this. I mean, what I just did right there, if you measure the thickness of that one, and then throw that line back to that vanishing point, there's only going to be one ellipse that will fit on that. And those ellipses will have to get progressively smaller. I chose to make these lines the right contour. If you made them the center, you'd have to shift things around. So you can do it by simply giving it some width and projecting the width back, and that would be a simple way. But you can run into some other problems that this third one will solve. For example, what if this was windows on the side of a skyscraper, and there's windows and then stucco, and then windows and then stucco, you know? And they're not the same measurement. It's not all equal. You've got one that's maybe 4 feet wide and one that's 3 feet or 2.5 feet. You can solve it with this, but I'm going to show you a new way. And it's based on what happens. Let me show you what I did here. Let's simplify this by flattening it out a bit, best I can. If you were making the mistake of trying to copy what I was doing, I suggest you stop copying and watch what I'm doing right now, because I'm going to go over this again and then make the next point. You ran a line from there to find that one, a line from there to find that one, a line from there to find that one, and you'll do so infinitely. What are these diagonal lines? They are these. What are these diagonal lines to each other? Parallel. Remember what happens when any lines that are parallel go away from us? What do? They converge. Where do these parallel lines converge? Which vanishing point? On the vanishing trace. Right, so if I go like that and run any one of these up there, it's going to make a point that all of these will converge at. That's kind of helpful. Because what I was doing is I was working from the inside out, doing these lines to go back in space. But now I see there's another way to do this. Let's get rid of that and try it again with the vanishing trace. And this is number 3, which I call vanishing trace diagonal. And it's got some advantages, which I'll show you. Vanishing trace diagonal means I've got to establish my first 2 lines, which we'll do this like so. Say that it's like that. And then run that diagonal like so. And I don't need to go through the middle or anything. And you'll see I'm doing a different angle now. Run that diagonal line up there. And if I can find the vanishing trace, which will be where? Can you see it up here? You're crazy if you're drawing this. Because this is in the books and you can copy it. If you want to watch somebody do it, you'll get it maybe for the first time. Vanishing trace, vanishing point up there. Now watch. That goes up there. All of them will touch that, so I can just start at this corner and run it up to that vanishing trace and then go down. Run that up to that vanishing trace and then go down. Run it up to that vanishing trace and then go down. And you see that I'm getting the same effect. And eventually what happens, they'll go to the line and they'll be all vertical because they're getting so close together that there's no distance between them. Now, here's the hassle. It's a drag that vanishing trace is so far up there, isn't it? Because I can't reach it. You know, it's really simple to bring the vanishing trace down. All we care about are these vertical measurements. So why not just take a section? Let's say we're going to do this, try to solve the same problem, and instead of having a vanishing trace up there, why not just say, use that section and see what happens? Look what we're doing. Use this section and do, oh gosh, that means that each one of those is going to have a parallel line like that. Run that through that corner, and now it goes there. Now what do? We go there, and it intersects there. We go there. Actually, I can go ahead and run that line back. There, and it intersects there. We go there, and it intersects there. Do you see what I've done? I can then erase these lines. I'm getting my divisions back in space. This doesn't just work for verticals. Take the board and go like that, and it works for floor tiles or railroad tracks or anything else. I mean, you can do that to figure out that if you've got parking meters on one side of the street, that there's just going to be a line across the other side of the street to give you the same division of those parking meters that go back in space. But I promised you something, and that was that you'd be able to do this to make unequal divisions. Right? That is, let's say that those are, what was the analogy I gave? Windows on the side of a building, and there's the width of the window is not the same as the width of the concrete or the stucco or whatever in between the windows. Here's how you do it. I'm going to work a little bigger here so that you can see this a little better because I've got to put more lines in it. But I'll try to make it severely enough in perspective to get the point. There's our, give me just a moment. I need to maximize my space here. That's our horizon line. That will be the area that we're trying to find on the side of that skyscraper. We're looking down from another skyscraper. And let's say the window is that. That is, we've got to know that somewhere, that division, right? Somebody's got to decide that line's going to be there. And let's say the space between the windows is that much. Now, there's a way we solve this. It always helps to go back to the side view and get the principle. The principle being that the window is like that, and the space between it is like that. I can use the vanishing trace to solve this problem simply, but I don't want a line like so because it's going to take my vanishing trace way up there, so I'm going to do the same thing, cut a little section out of that, and run a line like that for that one, and a line like that for that one. And that will hit a vanishing trace. Let's do it. That's got to go back to that vanishing point to be correct. That line and that line. Now I want to get a whole bunch of lines parallel to this diagonal parallel to this diagonal. You see why you have to know all this stuff we've talked about the previous years? Your brains are cooking. You want a bunch of lines parallel to that one and parallel to that one. How can you find them real fast? Go to the vanishing trace. The vanishing trace on that one's going to be right there. And then, how do you find this next one, which should be the same as that? Go to that vanishing trace. It'll be right there. How do you find that one? Go to that vanishing trace. Be up here. Connect it up there like that, and it'll be right there. You see that? How are you going to do the next one? Same vanishing trace for this one and this one. Right there. Connect that. It's going to be right there. Now we got to find one to match that one. It's got to point right up there. It's going to do it. It'll be right there. And you can make window, concrete, window, concrete, window, concrete. And that doesn't just work for lockers and sides of buildings that have windows. It also works if you take the thing and go like that, and then this becomes railroad tracks. And these are the, what are they, ties? The ties. And then this is the space between the ties. Now, was that exciting? Okay. Now, I found out this week that Watson's book, Creative Perspective, doesn't talk about this much at all. There's just a few allusions to it in when he's solving other problems. D'Amelio's book has a good deal on this. He's got 5 or 6 pages or more on this. And D'Amelio's book is very good at explaining. It's one of the best that I know of at explaining this. So Ernest Watson's book, great as it is, pretty much neglects these depth measuring systems. But he has a chapter, Watson has a chapter on floor tiles, in which he teaches you how to do different floor tiles, whether you can put them in, and that deals with some of these same vanishing trace problems, because remember, if you take the board and go like this, the vanishing trace becomes the what? The horizon line. And so really, you're doing kind of floor tile. Imagine that, right? You'd be able to just run lines and find the diagonals of every floor tile and solve that problem. So that would be a good chapter to study at the same time you're studying the depth measuring systems in D'Amelio's book. Now here is the trick to all this. The trick is, as it often is, get your perspective problem out of perspective. Get it flat, and then draw lines on it. Simplest lines that you can draw, and look for parallels and see where they'll converge. With this one, it's real simple, because this can be the top of a ping pong table. And if you take a paintbrush and actually paint those diagonals on the ping pong table so they can't wiggle, and tilt that ping pong table in that position, those lines are going to be right there, and you're going to be able to find that center, right? And you can start to divide that up any way you want, Do anything you want to, and then do the same thing. Straight lines are the simplest possible lines. Divide the same thing up here, run those lines around, and you'll find that the divisions work in perspective, because see, these get closer together, and so it changes the proportions. How did we solve the problem of, with the first one, of finding the center of the ping pong table is relatively easy, but what if we're trying to find that next corner, which doesn't just work with parking meters, it works with football fields. If we've got a football field in perspective, and we're trying to find that next corner, if you take it out of perspective, we saw, and I'm going to do it the opposite way, you've got a number of divisions here. You've got to find the absolute center of that, and run those diagonals and find. Run those diagonals through that line and find the next one. And you can keep doing that until you find the next division. If it works that way, what do you have to know? The first two, get a center line there somewhere, running back to the same vanishing point, and then that point, not that point. That's where beginners always make the mistake. They try to find the edge that they have already know where it is, but but you're trying to find this edge. Run that diagonal, and it will do the same thing that it did on the flat surface. And with the vanishing trace, how do you want to find the parallel lines just like we did there. We know that if we repeat this, let's just measure it out. That is like that. Make it the same distance, and we'll make that one like that. Same distance. We've taken it out of perspective and run lines like that, and we say, my goodness, those two are parallel. Those two are parallel. Therefore, they must converge at their own vanishing points. And you can then use that to find the hidden divisions. Any questions about this? Yes, Daniel?
If we're using the football field analogy, and we know we have this separated into 10 separate pieces, how do we know where to put the first mark?
There's a couple ways. There's 2 or 3 ways. One of the quick divisions you'd make would be what? If you want to divide it in half, so you're dealing with 5 instead of... Right? Just, yeah, and then you're going to know where the 50-yard line is. It depends on what you are committed to. If you are committed to that, that's the end of the football field. That's the front and that's the back. If you have to have that, then the 2 systems that I show you next week will be better. But if you could move this line, you can kind of eyeball it, or you decide how wide angle is my lens. If you've got a wide angle lens, that first 10-yard line could be right there, right? And if it's that wide angle of a lens, you're going to end up having to exaggerate this business, right? And that way there's going to be more severe reduction. But if you can decide on that first one and then do the diagonal lines and then be able to shift that back line, you'll be safe enough. If you have to get it exact, though, I've given you 3 systems. Next week, I'm going to give you 2 more systems, which are the 2 best systems. They have the fewest limitations. In fact, they really don't have any limitations for measuring things back in space. But in order to give them to you, I have to do 10, 15 minutes of explaining about what the theory is and show you it out of perspective and then do it in perspective. And it should be invigorating and exciting and should take years off your life. I mean, add years to your life. I'm sorry. Yeah. And they're in D'Amelio's book. One of them is to make a special vanishing point, a measuring line out of perspective, find a special vanishing point that it will go to, and just make non-perspective divisions and then throw them back to that vanishing point, and they'll hit right at the... It's the simplest and best way. But there's another way, and that is you design your own checkerboard. You design the edge of a checkerboard and then run a diagonal across, and then you can run the lines across, and you'll find exactly where everything fits according to the little plan that you drew. And I know I didn't explain it adequately, but I wasn't trying to. I'm just giving you a preview that there are 2 ways that will solve a lot of these problems next week. But you say, well, why did I give you these 3 if they aren't the best? Because it's nice to have 5 weapons instead of 2. Even if those 2 weapons are the best weapons there are, sometimes it's nice to have a Derringer. Even though a Derringer isn't that accurate, and it only comes in handy at close distances with your opponent. Sometimes that little X fine center thing comes in real handy when you're sketching, and you kind of want to just quickly, okay, oh gosh, it's further back than I thought it was going to be. Also, this gives us a chance to see whether you've understood everything we've said up to this point. Yes?
If you're drawing that football field, and like the football field,
there's
fit it in a page.
2 answers to your question. One is, you do this on tracing paper. You do it small on a piece of tracing paper and then blow it up on a copy machine, okay? That is the most logical solution. It's what you tend to fall back on after you've driven yourself nuts by trying to solve... Don't try to solve perspective problems on your big canvas. If you solve them on an 11 by 17 piece of paper about this big and then blow that up on your big canvas, then you can just copy those lines and they'll be close enough. Okay, I know this from experience. That's the first answer to your question. Solve it on tracing paper, small, and then project it. The second answer to your question is that I think that the 5th system next week, the measuring line and special vanishing point, might be the easiest way to do that so you wouldn't have to hassle with the vanishing trace. I mean, I'm working on this piece I'm doing where I've got all of these things in this garage. I've got all these robots and stuff in this garage. I've got some lines on the back wall that are going back in space, and I've got it. It's like doing a crossword puzzle, isn't it? I mean, I've got all these problems. It's like, how will I solve this problem? If I can solve that one, that will help me find that line, and if I can solve that line, it's quite a challenge. And one part of the challenge is determining whether you're going to use your thesaurus or your dictionary or ask your friend. And in solving the perspective problem, should I use a vanishing trace diagonal? Should I use a special vanishing point and measuring line? For this one, I'm using the vanishing trace diagonal because it's pretty quick. I put a line up here, and then I go, and where they disappear because they're going back into the fog. So again, 2 weeks, or next week, you'll have 2 more systems, and then you get to have the wisdom of the warrior to know which weapon to pull out of your arsenal. Then you'd have to look for other patterns. Yeah, that's true. Although it would work for a tree line, it works great for tree-lined streets. Any of these systems works fine for tree-lined streets because you only have to find one point, and there's enough variation in tree-lined streets to where you can just go from that point. And again, the most important thing is your composition. This is to help you solve problems. In D'Amelio's book, he's got rows of soldiers in the Civil War. And they diminish. I mean, you could tell it was a big job because there's about 100 soldiers in this picture, and they're in strong foreshortening, but they're all there, and they're there correctly. I mean, they look like they diminish back in space correctly, because he would have gone through and measured out, the basic space they'd fit in, and then eyeball it from there. But yes, all this perspective business is best understood according to man-made things because we are the ones that make right angles. And it applies to circles to some degree to nature. If you look at how the shadow wraps around the moon, as the moon waxes and wanes, it's an elliptical shadow, and it does the tricks that ellipses do. So there's some natural application, but somebody else going to ask something? I see another hand around here. Like always, I will tell you that this is to be learned so that you can then chuck it. But you have to learn it before you chuck it. If you want to get any, I found with me, when I'm doing stuff back in space, you can tell if a beginner tries to do this measuring back in space by eyeball, and then you check it, it's way off. But if you do this 6 times, 16 times in the next year, if you measure things out and you kind of, oh gosh, that's a little bit more whatever, you know what happens? You start to then freehand it, and it takes on an authority because you've been down that road and you know what that's like. And you can eyeball it with strength and say, I want it to be this way for my composition, and it's close enough and nobody will ever know. People don't usually take tracing paper and put it over your finished pieces and figure out the perspective. But they will know if you're trying to make it look accurate and you can't. They'll think it looks kind of weird, doesn't it? Anything else?